Hi, hello, welcome to part 3 of chapter 5 lecture. In this part, we are going to talk about ionic compounds and ionic bond. So before you go on and watch this lecture, again, I want you to make sure you're very much comfortable with Lewis dot symbols and valence electrons. Learning about Lewis dot symbols is important to understand this topic of ionic bonding and ionic compounds. So let's talk about what is an ionic bonding is. Ionic bonding basically refers the electrostatic attraction between positively charged cation and negatively charged anion. The electrostatic attraction between these oppositely charged species will hold these ions together, that we call it as ionic compound. So an example of ionic compound you see here is a sodium chloride molecule, a sodium chloride ionic compound. So as we discussed previously, there is a reason why metals lose electrons, which is to gain the electronic configuration to have the isoelectronic configuration with the noble gases. There is a reason why non-metals gains electrons. It is to have the isoelectronic configuration with its closest noble gas configuration. So they follow, there is a predictable trend as we discussed. Group number usually tells the number of electrons the metal is going to lose, and the group number for the non-metals usually tells how many electrons it is going to gain based on the distance between its group number and its neighboring noble gas electronic configuration number. So sodium has one valence electron because it is from group 1, and group 1 metals tends to lose those electrons to form the positively positive charge. And chlorine is from group 7. It is one electron away from group 8. So it would gain that extra electron to form negatively charged ion. So the positively charged ions we call in chemistry as cations, and negatively charged ions in chemistry we call them as anions. So these anions and the cations combine together by forming these ions to form a ionic compound. So ionic compounds again are made up of oppositely charged species that are attracted towards each other through electrostatic attraction. Okay, we are going to see what is that electrostatic attraction is in the next slide. So we can refer these chemical formula of sodium chloride as chemical formula, or sometimes just formula, or to be specific, sometimes you can refer it as ionic formula. So all of these things mean same. Means same. What it means is it basically tells us how many of each one of the element is present. In sodium chloride, there is one sodium and one chlorine, so you just write NaCl. But if you happen to have any one of these extra, you just use the subscript to include how many of them you were present. Chemical formula usually represents the total number of atoms the molecule has. So ionic compounds. In previous slide, I said that we have, excuse me. In the previous slide, I said that ionic compounds are formed as a result of oppositely charged ions attracted to each other through electrostatic attraction. So this is how it happens. This is a graphical image of how it happens. So before I go into that, let me just clarify what is a lattice is. Lattice is a three-dimensional array of an anion and a cation attracted together to form a solid. So this is the crystal structure of sodium chloride molecule, ionic compound, and sodium chloride molecule found to exist themselves in this array of sodium, chlorine, sodium, chlorine, sodium, chlorine. So it is unique to each ionic compound. So that unique structure, that we call it as a lattice. Lattice structure tells us how the ions arrange themselves to form the solid. That's what lattice is. So let's discuss how this lattice is formed. A lattice of ionic compound is formed when metal loses electrons to form a cation and non-metal gains electrons to form an anion. We discussed this in the previous chapter 4. Do you see the note? Do you notice the difference between sizes of the atomic radius? What's this ionic radius? The sodium atomic radius is larger than the sodium ionic radius. Excuse me. It is because it lost an entire shell by losing one electron. Whereas chlorine swells larger by gaining an extra electron, so it is larger. It is, you can even see it in the lattice structure. Chlorine as larger and sodium as smaller. They form this lattice structure by the attraction between sodium and chlorine ions. So these attractions, they carry some force between them, these cations and anions. So if you are going to break these attractions between them, you're going to need to apply energy to break these attractions. Think of them as two oppositely charged magnets that are stick together. Do they come off easily? No. Try pulling off the magnet that you attach to the refrigerator. Does it come off easily? No, because it is magnetically attracted to the fridge. The magnet is attracted to the fridge through its electrostatic attraction. So you just need to strongly pull it out. Just like that, these ions are attracted to each other through electrostatic attraction. So in order for you to break them, you need to apply energy. That energy is called the lattice energy. So it is the amount of energy required to convert 1 mole of ionic solid to its constituent ions in its gas phase. Now, basically, we're talking about how can you make them go back to its ionic state from the solid state. So it requires energy, and most of the times it requires lots of energy because ionic compounds are, attracted to each other electrostatically attracted together to form a strong ionic compounds. And one of the reason in the first place they form these lattice compounds is because by forming these ions, they become more stable. How do we know? Is that it is because they release lots of energy when these gas-phased ions converted to a lattice structure of ionic compound. Individual ions are not stable, so that's why they combine to form the ionic compounds. So you would see lots of heat released during that process. So what we are going to do in the rest of the lecture is calculate the lattice energy that is required to break bonding between ionic compounds to change its physical state, to break them into its individual ionic parts. So to identify that, to calculate the lattice energy, so you need to have the data of how these ions are combined in what ratio and in what charge they hold, and what is the distance between these ions when they form these ionic compounds. So here we are required to go back to chapter 4 material again when we discussed about ions and ionic radius and atomic radius. I will review those topics for you. So to calculate this lattice energy, you need to know the charges of the ions that are forming ionic compound, and you need to know the distance they were separated by. So these are the topics that I'm referring to that we discussed in chapter 4. In chapter 4, we discussed the trends in atomic radius and we discussed the trends in ionic radius. So in atomic radius, we said that atomic radius increases from right to left, and also it increases from top to bottom. Okay, so remember that there is a trend from top to bottom, it increases, and so is from right to left. And it mostly follows this similar trend in ionic radius, but you need to see, you want to see it in two. Let me separate that. But you want to, when it comes to ionic radius, you don't want to compare whole periodic table. You want to read the left side, the cations, and right side anions separately. So the trend here is that So red that you see is the actual size of the ion, and the large white gray you see is the size when it forms the anion. So nitrogen size is increasing from, so the size of the ions is nitrogen is larger than oxygen, than fluorine. And when it comes to the charges, when it comes to the ionic radius of the metal ions, ionic radius from left to right, it is decreasing. 102 for sodium, excuse me, I'm looking at the atomic radius. Let me look at the larger blue one, the larger number. When it forms, oh, excuse me. Yes, I need to have coffee. Let me correct myself again. So the larger blue one is the atomic radius, and the gray one inside is the ionic radius when it lost the electron. So ionic radius for sodium is 102, whereas ionic radius for magnesium is 72, and ionic radius for aluminum is 54. So it trends follows from right to left, it increases. And from top to bottom also, ionic radius is increasing as well. From magnesium to calcium to strontium to barium, ionic radius is increasing as well. So before I start this topic, I want to use this opportunity to review the possible ionic charges. As I said, metals will lose electrons depending on its group number. So all the group 1 elements is going to lose just one electron. Just one electron. And all the group 2 metals is going to lose 2 electrons. So these are the charges that we are talking about in that formula that we are going to use now. And all the group 3 elements is going to lose just 3 electrons. Those are the number of valence electrons that they will lose. And a group 5 element is 3 electrons away from group 8A. So it is going to gain 3 electrons. So -3, -3. And a group 6 is 2 electrons away from group 8. So it gains 2 electrons whenever it required to gain electrons. Group 7 is 1 electron from group 8. So it gains 1 electron only. So these are the possible charges that you're going to need to use to calculate the lattice energy, the energy required keeping these ions together. So here are the lattice energies for different ionic compounds and their melting points. You don't need to by heart them. You don't need to remember these numbers on top of your head, but you need to remember the trends in these set. So lithium, when making bond with fluorine, bromine, iodine, there must be some trend, right? Same element making bonds with fluorine, chlorine, iodine from same group that have different atomic radius and same charge. So there must be some trend. So the trend here is that the lattice energy is decreasing in that set. And let's look at another case. Sodium, when making bond with chlorine, bromine, and iodine, and there should be some trend again. The trend is that lattice energy is decreasing as the ionic radius of halogens are increasing from chlorine to bromine to iodine. And again, you can see the same trend here. Potassium, when making bond with chlorine, bromine, iodine, and you see that according to the trend, the lattice energy is decreasing. So that is how I'm going to test you, whether you know the difference between lithium fluoride lattice energy and lithium bromide lattice energy without remembering these numbers based on this formula of F is proportional to the charges of lithium and halogen over the distance between these ionic radius. Based on that, we are going to predict these lattice energies. And the use of melting point included here is to know that the melting point is directly related to the lattice energy. Now, what is a melting point is when a substance converted from solid state to a liquid state. So why it changes its physical state form is when you provide enough energy to disturb its lattice structure, it will grow from its solid to liquid form. And it is taking lots of temperature to break its solid state to a liquid state. That's why these numbers are in hundreds and even some of them are in thousands. Most of the covalent compounds that they melt pretty easily, water boils at 100 degrees Celsius. Here you see like 800, 500, 400, 600, 700, much larger numbers, which means lattice energy is much more prevalent, much more stronger in ionic compounds. Now let's practice calculating the lattice energy, the numbers that you just saw here in this slide. We're going to calculate lattice energy for some of these molecules, so you will know how we got those numbers. All right, let's calculate first for lithium iodide. So lithium has +1 charge because it is from group 1, and iodine has a -1 charge because it is from group 7. So if you try to calculate the the electrostatic attraction between them, it is calculated as the +1 and -1 over its atomic radius of lithium, which is 0.76, and atomic radius of iodine, which is 2.20. So when you calculate that, you would end up with the force between these electrostatic attraction force between this lithium and iodine as 0.11. Let's calculate for sodium iodide. Why? Because we are trying to do a study between same group and the same group element with the same element. So lithium and sodium are from same group 1, but iodine is a single element. So we're using it as a study. So when you do that, the only difference between sodium and lithium is that its ionic radius. So ionic radius of sodium, because it is a larger element, is larger than the ionic radius of lithium. So the electrostatic attraction force between sodium and iodine is much less, a little bit less compared to lithium iodide. And what happens if you had much larger element from the same group compared to lithium and sodium? So potassium, the next element in the group 1 after sodium, has much more larger atomic radius compared to lithium and sodium. So it has less electrostatic attractions between those ions. So as you see, the electrostatic attractions between these ions is directly related to the lattice energy. The larger attraction, larger the lattice energy. Smaller compared to lithium iodide, so smaller lattice energy. Much smaller attraction between the ions and much more smaller lattice energy. Let's look into one more study. Okay, let's look into lithium fluoride case. By this time, you know how we are getting these numbers. We are getting positive and negative ionic charges, and these numbers are calculated values. They're basically atomic radius of lithium and the fluorine. So when you calculate the lattice energy based on the electrostatic force, you got some lattice energy in thousands. Let's say you have elements from group 2 and group 6. Okay, what difference it makes? So compared to elements from group 1 and group 7, which we have here, group 1 and group 7, let's see what happens if you had elements from group 2 and group 6. So group 2 has +2 charge and group 6 had -2 charge, and there the atomic radius is 0.72 and 1.40 respectively, and when you calculate the electrostatic attraction between them, it happened to be 0.89, which is much more larger than 0.23. So what it says is, higher the charge, higher the electrostatic attractions between them. So does the lattice energy indicate the same? Here you have lattice energy of thousands, and here you have lattice energy close to 4,000. So it does indicate the same. Greater the charges, greater the lattice energy, because greater the electrostatic attraction force between the ions. Let's look into another example. So here what we have is an element from the cation from group 3 and anion from group 5. So group 3 metal is going to have +3 charge, and a non-metal from group 5 is going to have, excuse me, I wrote 6 there. And a non-metal from group 5 is going to have -3 charge. And if you calculate the electrostatic force between them, the electrostatic force between them is happen to be much more larger than the previous two, and it does shown in the form of lattice energy as well. So what do we know so far is that when ionic compounds are formed, they form because the electrostatic attractions between the positively charged cations and negatively charged anions. And you could actually calculate these electrostatic attraction forces between them if you know the charges they were holding, both the cation and anion, and if you know those atomic radius of those elements. And those are directly related to the lattice energy values. Higher the electrostatic force between them and higher the lattice energy directly indicates how stable that particular lattice structure is. So higher the lattice energy means higher the melting point. Now let's apply what we learned so far. So the question is asking, arrange magnesium oxide, calcium oxide, and strontium oxide in order of increasing lattice energy. Okay, so it is asking you to arrange them in increasing lattice energy order. So what do we do? Let's look for commonalities. The commonalities is that you have oxygen in all of them, right? In magnesium oxide, calcium oxide, and strontium oxide. And magnesium, calcium, and strontium. Look in the periodic table, find where they were present, see if you can find any trend. If you look in the periodic table, you can find all three of them in group 2. They all belongs to group 2, and they were one after another. So magnesium is smaller of calcium, smaller than calcium, and calcium is smaller than strontium. So they were from magnesium to calcium to strontium. So when they all hold same amount of charges, like a magnesium, calcium, and strontium, but they have different atomic radius. There should be a clue. Remember the formula that we are going to use. Force is directly proportional to the charges between them over the distance between them. So when the charges are similar, because the distance is in the denominator, higher the distance between them, lower the force is going to be. Smaller the distance between them, larger the force is going to be. So between magnesium, calcium, and strontium, magnesium is the one with the smallest ionic radius compared to calcium and strontium. So which one is going to have a largest lattice energy is the one that has the smallest ionic radius when everything else is common. So magnesium oxide should have the largest lattice energy compared to calcium oxide and strontium oxide. Okay, that's all from this part. I'll see you in part 4 of the lecture.